I'm going to review some work from various groups on modeling the dusty star-forming galaxy population. Historically, the focus here has actually been on sub-millimeter selected galaxies, but I mean, a lot of this translates over to infrared selected galaxies. Um, Also, and the same questions are really relevant. So I apologize that it's more focused on the sub-millimeter, but it's definitely a lot of the same questions we're asking. What I'm showing on the title slide here, this is just from a recent work from Rachel Cochran, who's a graduating student of Philip Best at Edinburgh, and she'll be doing a joint postdoc. She has a John Harvard Distinguished Fellowship at CFA, and then also a Flatiron Research Fellowship here. So she has a 4-year position. I'm excited to continue working with her. And she's actually an observer, but has been moving into theory. And so those of you who work on infrared luminous galaxies, definitely look out for her. She's amazing. So, wrong button here. So first, I'm going to talk about why modeling dusty star-forming galaxies is hard. And throughout this talk, I'll be referring to bright submillimeter selected galaxies or dusty star-forming galaxies. So think luminosities of greater than of order 10 to the 12 solar luminosities, or submillimeter flux densities of at least a few millijansky. So these are very bright, very extreme sort of tip of the iceberg objects that people have been interested in modeling, because for many years that's all that we were observing. So why is modeling this population hard? Well, one thing is that these objects are very rare. So we're talking about a few times 10 to the minus 6, maybe 10 to the minus 5 per cubic megaparsec co-moving. And so if you want to model these with a hydrodynamical simulation with the full cosmological context, you need to run a large volume simulation. The problem here is that if, as is been commonly assumed, not comically, maybe there's a Freudian slip, but as has been commonly assumed based on analogies with local ultraluminous infrared galaxies, if these are indeed compact starbursts driven by mergers, then the issue is you need to have very high resolution. And in general, of course, you want very high resolution to be able to model the structure of the interstellar medium. But especially in these cases, if you look at ARP 220, where of order half the luminosity comes from a region that's smaller than something like 50 parsecs in size, or coming from those two cores, compact cores, you need to be able to resolve the tidal torques and those compact star-forming regions. So that's extremely challenging to do with large volume cosmological simulations. And then furthermore, if you actually want to compare with this observed population that's selected in the submillimeter or infrared, you need to worry about the mapping between the physical properties of the galaxies and the quantity with which you're selecting the population in real observations. And I'll talk about that in some detail. So first, I'll talk about work with semi-analytic models. For those of you who aren't familiar with these, very briefly, the idea is you start with merger trees, either taken from a dark matter only large volume n-body simulation, or use the extended Pressure formalism. Aaron Young will give us a much more detailed discussion of SAMs later on. And then you have a set of recipes or simple differential equations where you have hopefully physically motivated prescriptions to account for things like star formation and stellar feedback, but you're not computing as much directly as you are in hydrodynamical simulations. So an early semi-analytic model that looked at the submillimeter selected galaxy population is from the Durham group, the Galliform model. What they did when the first submillimeter surveys were coming out from single-dish telescopes in the late 1990s and discovering this population of bright submillimeter sources with inferred star formation rates of hundreds or thousands or even of order 10,000 solar masses per year, they went to their models at the time and they said, well, do we expect such a population to exist? And it turned out that the model, which was Granado et al. 2000, they underpredicted the counts very significantly. So over 2 orders of magnitude. They said, well, this is a problem for us because we've developed this model that agrees well with constraints like the present day stellar mass function, but we're completely wrong in the submillimeter. So what can we do to our model to not break the agreement with these constraints like the redshift 0 stellar mass function, but still match these submillimeter number counts? So they tried a lot of things because the tuning in this case, and still in many cases, is a bit of black magic, just by hand tuning, adding things into your model, tuning the parameters, seeing whether you agree worse or better with observations. So they tried a lot of different things, and what they found is that the only way of the modifications that they tried, the only way they could match the observed submillimeter counts was by changing the initial mass function in starbursts. So in this model, there's two modes for star formation. One is just normal quiescently star-forming disk galaxies, and one is starbursts that are driven by mergers. And so what they assumed is that in the normal star formation in disks, they have just a standard Milky Way type IMF, a Krupa IMF. Whereas in the merger-induced starburst, they have the IMF given here. dn d log m is constant. So this is very top-heavy because with the standard Krupa or saltpeter-like initial mass function, the slope at the high mass end is minus 1.35. So this is way more top-heavy than you have with for a Milky Way-like IMF. The reason that this helps you is for a given unit of stellar mass formed, if you have a more top-heavy IMF, specifically the flat IMF here, you have about a factor of 2 more luminosity, but even more importantly, you have a factor of 5 or 6 more metals produced and thus more dust. And so your resulting SED, because of thermal equilibrium, is colder, and so your ratio of submillimeter flux density to star formation rate is much higher when you assume this IMF rather than, say, a Krupa IMF. So what this plot shows is if the model with the dashed line is the submillimeter cumulative counts, if you use a standard Krupa IMF in the starbursts, whereas the solid is their fiducial semianalytic model where they use this flat IMF for starbursts. You see in that case, they predict the accounts, and it makes almost 2 orders of magnitude difference in the predicted counts. However, this was very controversial because there's definitely no observational evidence for an IMF that is this flat, and observers are reluctant to take semianalytic modelers' statement that my model doesn't match observations, therefore your IMF must be wrong, to take that too seriously. So this is something that there's been a lot of work about this. So actually, the most recent version of the Gelform model, about 10 years later, from Laciel 2016, this conclusion has changed drastically, and I should actually mention in the Bog et al. Model, SMGs are predominantly minor merger-driven starbursts in which the more massive galaxy in the merger has a gas fraction of at least 70%. Whereas in the most recent version of the Gelform model, SMGs are now predominantly normal disk galaxies that are gas-rich, that are undergoing catastrophic fragmentation from gravitational collapse because they're unstable disks. And they have a much less top-heavy IMF. So they still have a top-heavy IMF in these starbursts, but it's dn d log m, the slope is -1 rather than 0. So it's only slightly more top-heavy than, say, a Kennicutt or saltpeter or Krupa IMF. And what these plots show are the cumulative number counts. This shows the effect of changing the high mass slope of the IMF. You see their prediction is still sensitive to this. Whereas on the right, this is the number counts for different assumptions about whether mergers drive bursts, and you see it makes absolutely no difference whatsoever. So in the current Gelform semianalytic model, mergers are completely irrelevant for the bright, dusty star-forming galaxies. However, not all semianalytic models require IMF modification. So this is some work that was led by Mohammed Safarzadeh using Yu Lu's semianalytic model. And the only thing I want you to take away from this is that in this fiducial model here, depending on how we translate the properties of this model galaxies to submillimeter flux density, we can actually get reasonable agreement with the observed submillimeter counts despite assuming a Krupa IMF here. So I would say the jury is still out, and part of the problem is here, as Aaron will probably tell you about, is there's a lot of free parameters in these models. There's a lot of alternative ways you can treat things like stellar feedback. And so even for a fixed model, if you don't fully explore the parameter space doing something like a MCMC search, then what you may find is you get a model that seems to work reasonably well, but in some other region of that multidimensional parameter space, you could have an equally good model that doesn't have a different IMF than Krupa. So this requires more careful modeling, and it's still an open question for semianalytic models. So now moving on to hydro simulations. I'll first start by discussing idealized hydro simulations, and what I mean here are simulations that are not cosmological in nature, just creating idealized disk galaxies, perhaps colliding them together. And then we have ways of putting these in a cosmological context, but they're fundamentally different than, say, cosmological zoom simulations or large volume cosmological simulations, where you have the large scale structure of matter included, and you have things like inflows. Um, so I'll talk about those after this. So this is a lot of the work that I did during my thesis and afterwards, was using these kind of simulations to see whether we could reproduce these really bright infrared luminous galaxies. This plot on the left here shows the 850 micron flux density versus time for a equal mass merger of two galaxies that have stellar mass of order 10 to 11. So these are very massive gas-rich galaxies. On the right, you have the star formation rate. So what you see is that you have a strong peak in the star formation rate, about a factor of, I think it's 10 or so enhancement in the star formation rate. And during that same time, you have a strong peak in the submillimeter flux density. And this is showing from a follow-up work, a more detailed plot. I won't go into that in the interest of time, but basically in a series of works, we found that consistent with what observers inferred based on early observations and with analogies with the local ultraluminous infrared galaxy population, mergers do drive strong starbursts, and you can get a boost in the submillimeter flux density from this. But what I actually found was that the boost is much less than you expected. So the relation between the submillimeter flux density and the star formation rate is highly sublinear. And part of the reason for this is that you have temperature evolution, that at the time of the strong starburst, you have a sharp increase in your luminosity heating the dust, and you actually have a decrease in the amount of dust that is in the gas phase because of gas consumption. And so your SED becomes hotter. Your peak shifts to shorter wavelengths, and so this partially mitigates the boost in submillimeter flux that you would get if you kept a fixed SED shape and just increased the total infrared luminosity with the star formation rate. I keep hitting the wrong button. So what we did is we created a sort of hybrid model that relied on a semi-empirical model to put these idealized simulations in a cosmological context in order to predict the number counts and redshift distribution of bright submillimeter galaxies. This is showing the resulting number counts from this model. You can focus on the solid line here, which is the total number counts, and this is comparing to various observations. And one of the assumptions in this model is we just took the stellar mass function at different redshifts. We just took that as an input, okay? So this is not an ab initio model, not a large volume cosmological simulation where you just can predict the number counts without doing anything else. We had to do this kind of hybrid approach. And so what we found is that when you do reproduce the overall galaxy stellar mass function, then you sort of just naturally get out the submillimeter counts, assuming the results from our simulations. And I should have mentioned previously, the way that we predict this is that we do Monte Carlo radiative transfer calculations in post-processing. So you take your hydro simulations outputs, you take the light from the stars and the black hole particles in those, you propagate those through the dusty interstellar medium, and you actually make predictions for the UV through millimeter SEDs, or if you want to, IFU-like data cubes. So we find this good agreement. From these simulations, what we found is that the types of galaxies that dominate the counts, they differ as a function of the flux density. So at the highest flux densities, you have that these are the sort of classic picture of late stage major merger-driven starbursts. At the fainter flux densities, you have just massive isolated disk galaxies that aren't undergoing mergers. And then at all flux densities, you also have this contribution from blended galaxies, galaxy pairs, where they're mergers in earlier stages that are not yet undergoing strong starbursts, but because of the large beam sizes of the submillimeter single dish telescopes, 15 arc seconds or so, you blend these into a single source. And I'll talk about that a little bit more later if I have time. Okay, so now moving forward to cosmological zoom-in simulations. So as I was describing, the fundamental difference between these idealized simulations I just discussed and zoom-in simulations is in the former, you just create a galaxy by hand with sort of reasonable properties based on observations, and then you collide two of them together to see what would happen in the merger, but you're not forming that galaxy self-consistently. Whereas in the case of cosmological zoom-in simulations, you run some large volume, low resolution dark matter only simulation. You select halos of interest. So for this work, we were looking at halos that ended up having high masses, so something like 10 to the 13 already at by redshift 1, because those are what we think, based on observations, those would host bright infrared luminous galaxies. And then you go ahead and you resimulate the sufficiently large region to capture that halo and any satellite galaxies that are going to collapse with it by redshift 0. You simulate that with hydrodynamics and stellar feedback, black hole accretion if you want to, et cetera, et cetera. And so this kind of resimulation, it has power over these idealized simulations that it can include things like gas inflows from the IGM. But it's, of course, much more expensive than these idealized simulations. So you end up not running as large of a number of these. So this plot shows one example of one of these very massive galaxies, submillimeter bright galaxies, from a cosmological zoom-in simulation, going from redshift 3 down to redshift 2. And what we found in this work was that this particular halo could be very bright in terms of infrared luminosity and submillimeter flux density, and that in many cases, the bright periods in the submillimeter flux density, they did not correlate at all with major mergers. It was just a massive galaxy that was undergoing bombardment from smaller satellite galaxies and just generally unstable because it was very gas rich, so undergoing fragmentation. And then you have from the stellar feedback that's implemented in here, this is from the fire simulations for those of you who've heard of those, but I won't go into any detail about that here. The stellar feedback, it causes this sort of cyclical pattern where you drive strong outflows, but then a large fraction of the gas that is kicked out of the disk ends up raining back down in a galactic fountain, increases the gas surface density, the disk becomes unstable again, fragments, and so you can have bursts that are just driven by this feedback galactic fountaining cycle. And we found that this was important for this particular simulation. So you see here, this is showing different quantities for the simulation that's visualized on the previous page, on the previous slide. The most relevant is here is the submillimeter flux density versus redshift, and then here is the star formation rate versus redshift. And so what you see is that the submillimeter flux density, it increases almost monotonically, and it jumps around a bit as you have these bursts in star formation, but it correlates pretty well with the star formation rate, and both increase with time as this galaxy becomes more massive. And what this plot shows is that for most of the time, when this galaxy is very submillimeter luminous, it's right around the so-called main sequence, the star formation, the relationship between the star formation rate and stellar mass of galaxies, that most star-forming galaxies fall within this relationship, and it's rather tight, something like 0.3 Dex scatter. And so the interpretation here is that this galaxy is not some strong starburst, it's just forming stars at kind of the rate you would expect for normal star-forming galaxies at redshift 2, around redshift 2. And that by inferring from this one simulation, we would argue that the bright DSFGs are just representing the high mass end of the main sequence, and consistent with that most recent version of the Galliform model, that mergers are actually not very important for the population. However, in this work that I advertised on the title slide by Rachel Cochran and also by Li-Chen Liang, another student working in our collaboration, we were interested in looking at how the dust continuum emission, how it traces the spatial distribution of different physical properties of the simulated galaxies. And one of the things we got out from that for free was just the submillimeter flux density and infrared luminosity. And this was for the simulations drawn from the same fire simulation project with a slightly updated form of the stellar feedback models, but slightly more massive halos, so going down about 0.5 Dex in halo mass. One of the interesting things we found in this work was that the highest submillimeter flux density we got was something like 2 millijanskis or so. So we didn't go that much down in halo mass, but we went down a lot in the submillimeter flux density, where you see in this work you're getting some of the brightest, if this galaxy is as bright as essentially the brightest submillimeter galaxies that have been observed in the universe. And so this gave us a bit of pause where now we're examining more carefully. We want to rerun the halo that was shown in the previous work with this updated feedback model that also used a different radiative transfer code. So we're trying to understand these differences because it seems that there's very steep dependence on halo mass. This surprises me at least. So again, this is still an open line of research. So now moving on to large volume cosmological simulations. As I said, this is kind of the best that you can do, the holy grail of modeling this population. If you can simulate a large enough volume to capture many of these rare bright infrared luminous objects. And you can also use high resolution so that you can capture the tidal torques and mergers and resulting starbursts. You can capture the clumpy interstellar medium and do the radiative transfer properly. That would be ideal. But unfortunately, even with the best simulations to date, so say like the illustrious TNG simulation or the Eagle simulation, your spatial resolution is still of order kiloparsec or a few hundred parsecs. And so you can't really capture these tidal torques. You can't really reliably do radiative transfer. So this has still hampered progress on this front. But I'll tell you what's been done so far and sort of what's to come. So one of the early works that looked at the submillimeter galaxy population in such simulations is from Ramil Dave and collaborators. What they did is they took a simulation with a volume of order 100 megaparsecs cubed. They made the assumption, they said, well, I know the volume of the simulation. Let me assume that I should match the observed number counts. So I can expect something like 40 bright submillimeter galaxies in my volume at redshift 2. I'm going to make the ansatz that the 40 most rapidly star-forming simulated galaxies should be the analogs of the 40 submillimeter galaxies I would see in the simulation if it were the real universe, and I'm going to look at their properties. So this is showing the 4 brightest. On the top, you see the stellar surface density. On the bottom, the gas surface density. And the conclusion they took away from this comparison is that most of their SMG analogs were not undergoing major mergers. They were just these very massive gas-rich galaxies that were often undergoing minor mergers because at redshift 2, you have small galaxies falling in all the time on halos of this mass. Some of the brightest galaxies were undergoing major mergers, but this was really something that was relatively uncommon. That was a minority. Some of the properties of their simulated galaxies agreed well with those of observed submillimeter galaxies. However, one of the big issues is that if they looked at this so-called star formation main sequence, this relation between the star formation rate and stellar mass of galaxies, what the observed relation is shown as this cyan line with the scatter indicated by the dashed line. So that's coming from large samples of galaxies, not specifically infrared luminous ones. The red dots here with the red line are what they have for the simulated galaxies. And then the points up here focus specifically on the submillimeter galaxies. So the green ones are the analogs in the simulation, given that ansatz about the simulated galaxies with the highest star formation rates being equivalent to the submillimeter galaxies. And then the points with error bars are the locations of observed submillimeter galaxies in this plane. And so what you see is that there's about a factor of 3 disagreement between the star formation rates at a given stellar mass with the simulations and the observed galaxies. But then, moreover, this is actually not specific to the submillimeter galaxy population. This occurs for galaxies at all masses shown in this plot, and this is actually a generic problem with this simulation at around redshift 2. And with many simulations, even today, they underpredict the normalization of this star formation rate stellar mass relation. And so one thing that Ramil discusses in this paper is that potentially the reason for this is that the observed galaxy star formation rates are overestimated, because when you get a star formation rate from an infrared luminosity, let's pretend you can get the infrared luminosity perfectly, you still need to assume an IMF in order to go back to the star formation rate. And so they typically assume something like a Krupa IMF, whereas if the IMF were actually top heavy in those galaxies, that means that by assuming Krupa, you would be overestimating the IMF. And so if this were true, you would bring these star formation rates down in agreement with the simulated galaxies, but you would need this to be the case across all masses shown here, not just for these bright, extreme infrared luminous galaxies. So work that hopefully will be submitted soon that I've been doing in collaboration with Martin Spar, who's a postdoc at AIP in Potsdam, and many others in the illustrious TNG collaboration. We've tried to revisit this question. So the illustrious TNG simulation is the improved form of the illustrious simulation, stands for the next generation. Basically, what happened is they had the illustrious simulation. It had a lot of successes, a lot of agreement with various kinds of observational constraints, but there were some issues. For example, there wasn't a good color bimodality, so it seemed that galaxies were not being quenched sufficiently well by redshift 0. And so the team went back and made some modifications to the models for stellar and AGN feedback in order to get better agreement with these observational constraints that they weren't matching well, and not to break the agreement that they had already. What we do in this work is we essentially bootstrap off the results of these idealized simulations so that we can do sort of cheaper version of radiative transfer in order to predict submillimeter flux density. And then we look at the resulting counts that we get out for both the TNG simulation and for illustrious. What you see here is that actually, unfortunately, the next generation is worse than the old generation when it comes to matching the submillimeter number counts. So the solid black line is for illustrious TNG, and then the dashed blue line is for the illustrious simulation. And then the points with error bars are some recent number counts coming from ALMA. So this is something that Martin was actually leading this project originally, but he got a little bit disheartened and he felt that this would be a politically unpopular answer with the TNG team, that actually the next generation is not as good as the old generation. But this is only for this specific relatively minority population. Overall, for the general galaxy population, TNG matches the properties better. And I actually look at this and I find this as an opportunity because one of the issues is that in these large volume simulations, and even in Zoom simulations just in general, you're not resolving all of the relevant physics. You can't put it in an ab initio manner, so you use these so-called subgrid models. And the way that you test these models is by comparing with observational constraints and try to test and refine them in that way. And so what I view these results as telling us is that actually this infrared luminous galaxies, they provide us with a useful additional constraint on models. And using the method that we use here, it doesn't cost any additional computational cost. It's a negligible expense in order to calculate the submillimeter flux densities. And so you can very easily, as you're running the lower or smaller volume simulations, when you're trying to improve your subgrid models, you can very easily make plots like this and compare with observations, and that gives you an additional useful piece of information besides what people traditionally use, like the stellar mass function. So the nice thing about illustrious TNG and illustrious is that although the subgrid models have changed, and I mean these are expensive simulations, requiring of order 100 million CPU hours. So this is not something you can't just rerun the simulation and say, well, I wonder if I make my AGN feedback weaker, what will happen? I'll just go rerun it, right? You kind of get one shot once you've fixed your model, and then you have to live with it until you get another grant and wait a few months or years running on many thousand cores, right? But the nice thing is that they decided for this reason to use the exact same initial conditions for TNG and for illustrious, and only to vary the feedback models. So by comparing these two simulations, if you look at individual halos, you can match them between the simulations, and you can get a sort of not apples to apples, but a direct comparison for that given halo. How did those variations in the feedback model affect the galaxy's properties? So that's what we did here. What you see on the left is showing the distribution of gas masses of the high mass, these bright submillimeter galaxies. In illustrious TNG is the blue histogram, and illustrious is the orangish one. And then the plot on the right is showing the positions in the star formation rate and dust mass plane. And this is for the galaxies that host bright submillimeter galaxies in illustrious, and their positions in the plane in illustrious are shown as the blue points. And then each of these halos is connected to the corresponding halo in illustrious TNG by the lines, and then the position is shown as the black points. And so what you see from these two plots is that if I have some high mass halo in illustrious that hosts a high mass galaxy and is very bright in the infrared and submillimeter, in many cases, it has a much lower star formation rate and a much lower dust mass, and the main reason for this is having a much lower gas mass in the illustrious TNG simulation. So what this and some other lines of evidence that I won't discuss in this talk in the interest of time, what this indicates is that in the team's interest of making the quenching more efficient to get a good color bond modality at redshift 0, what happened is that there was actually they kind of overdid it in some sense in that you're quenching massive redshift 2 galaxies too early. And so as a result, you're not getting enough bright submillimeter galaxies. And it turns out that actually at higher redshifts, say around redshift 3 or so, in some work that's being done by Valentino and E.R.A. Davidson and collaborators, they compare with the illustrious TNG and illustrious predictions, and we find we reproduce the number counts of those high redshift submillimeter galaxies and also quench galaxies. So it seems that the quenching is really sensitive to when exactly in cosmic time the quenching is occurring. So we've actually had some successful predictions, but in the interest of time, I'm just going to skip through this part because the timer I have, or how much time? The timer went, but we want to know the answer. Well, so the one potentially successful prediction from all of this previous work that I mentioned is we expected that there would be a lot of these submillimeter single dish sources would actually break up into multiple sources when you looked at them with interferometers. So you have not only these sort of galaxy pair intermediate stage mergers, but you also have the case that you can just have chance projections along the line of sight, right? Because of the negative K correction, you're sensitive to a very large range of redshifts. And so if you have two galaxies that are close in projection on the sky, but widely separated in redshift, those could be blended into a single source in the single dish submillimeter telescopes with the large beams. And so in some work with Peter Baruzzi and collaborators, we modeled this using a n-body, large volume n-body simulation and then a semi-empirical model to populate it with Mach submillimeter galaxies. The punchline is that you see essentially a bimodal population. This is showing the redshift, the logarithm of the redshift separation of the components of these blended single dish sources. And what we found is a roughly 50-50 split that some fraction of them are physically associated, so mergers or groups of galaxies, and then some fraction are widely separated in redshift with a median redshift separation of order 1. And these are just chance projections that have nothing to do with each other physically, but they would be blended into a single submillimeter source in these single dish telescopes. And the Durham group, the Galform semilytic model, some work led by Will Cowley, who is a student in that group, they found a qualitatively consistent conclusion, but they actually found that the chance projections dominated the blended submillimeter galaxy population. So I went out to test this with observations in collaboration with Chuck Steidel and Scott Chapman and others. We did follow-up of a small sample of blended sources with LRES and MOSFire in order to detect nebular emission lines and to see whether indeed the components were at the same or different redshifts. The punchline here is for a sample that's of order 10 galaxies or so, including our own and some galaxies from the literature. We find a qualitatively consistent conclusion that sort of order half of them turned out to be at different redshifts. You see one example here where one of the components is at a redshift of 2.2, one is at 2.36. There's some even more extreme examples. And this is consistent with other analyses from Wardlow et al., which is based on CO emissions. So one of the issues looking with for something like H alpha is giving the high dust obscuration, you could very easily not detect a line, not because it's at a different redshift, but just because the line is heavily dust obscured. With CO, you don't have that problem. So I was glad that Wardlow and collaborators found consistent results. And then also for 250 micron selected sources, some interesting work from Gillian Scudder also finds that these kind of chance projections provide significant contamination to the population. All right, now I'll just put up my summary. The basic take-home point that you all should take here is that these dusty star-forming galaxies with high luminosities, high star formation rates, they continue to give theorists a lot of trouble, and I would say theorists are paying more attention to them for this reason. It was a little bit of a cottage industry for a while, but more and more people are caring about these galaxies, and so we continue to be interested in kind of trying to improve the models in order to better understand exactly what this population is, what drives these very high infrared luminosities and submillimeter flux densities. And current models, they still have completely different answers for the population, whether mergers matter or not, whether the IMF is top heavy. So there's a lot of interesting work still to be done, I would say. Thank you.